Okay, you can go.
Okay, awesome. Good afternoon, everyone. Welcome to session 8 of ICMP 2020. This session is and has everything to do with programmable networks. So we have, like Sergey was saying, we have 3 papers with 2 presenters. Congratulations on having your papers accepted. We have Heng and Chen. Chen and his co-authors have 2 papers accepted, and he'll be presenting both of them, the second and the third paper. Housekeeping rules, like you all heard Sergey. Let's just do the audio for questions after the presentation is done, and it's worked out well so far. Hopefully it'll work well for this session too. So Heng is an assistant professor at the Institute of Computing Technology at the Chinese Academy of Sciences. He is broadly interested in software-defined networking, programmable switches, and distributed systems. He will be presenting our first paper, which is misconfiguration checking in programmable networks. So Heng, you can start your presentation and take it away.
Okay, thank you.
You're welcome.
Hello everyone. I'm Heng from Institute of Computing Technology, Chinese Academy of Science, and I'm going to present our work with configuration checking for SDN, data structuring service, and algorithm. This is a joint work with University of Zhou. First of all, I will introduce the background of this work. The context of this work is SDN, as well known. SDN separates the control plane from the data plane through open source APIs, such as OpenFlow. This separation not only can simplify the network management, but also enable network innovation, both in control plane and the data plane. However, you still had to develop and maintain a complex SDN application. To address this challenge, recently, network researchers began to borrow the thought of modularization to program the network and introduce convolutional SDN. Consequently, a complex application consists of multiple simple policies such as net, monitor, firewall, and so on. Network administrators somehow compose these policies by different convolutional operators to perform one complete network function. Unfortunately, convolutional SDN is available for 2 reasons. First, individual SDN policies have already been complex. This is because one SDN policy may contain 1 or more flow tables, while each flow table consists of a priorities list of flow entries. However,
Heng, sorry for interrupting, but we can see only your summary of your presentation. Can you go to presentation mode? Because right now we see only your title slide.
Only your text?
Yeah, so you don't you're not in presentation mode now. So we see the summary of the slides on the left.
It's okay now?
No, still the same.
Leonardo, I think we had this before as well, this problem. So maybe
we can switch to Zoom. I don't know.
Yeah, it's better if Heng will present the slides through Zoom.
All right, we share the link in the chat session.
Okay, I will switch to.
I've copy pasted the link in the chat window.
Yeah, I think on time we're doing actually fine because talk's only 20 minutes long, and so far there were not too many questions with attendance not being particularly high. So I think, and we have also the buffer time after this session, so 1.5 hours. So if we even spill out a little bit, it's okay.
Okay.
So let's see whether this Zoom will work for the presenter better. I think now we can see only the black screen.
Yep, I confirm. I can see only the black screen. Where are you connected, Heng? In Wova or Zoom now?
I think that's a repetition of my own presentation disaster from 2 days ago. So it's maybe some combination of the computer, like MacBook Pro and Hoover. Well, the first version was better.
Heng.
Another option for everybody go to Zoom, but maybe you can go and just to see not the presentation mode.
I'm in Zoom, but I cannot see everything.
So the sharing worked okay, right, before the session?
Yeah.
Okay.
But can you see, for example, my screen now? Because I'm sharing it.
Yeah,
Yes.
I can see.
Yeah, exactly. So, okay, I will stop to share. So I think that is a Heng problem in this case.
Well, it's all of us problem, right? So I think we're all in the same boat.
No, in the sense that probably he is not connected through Zoom.
Okay, so Zoom is for some reason not working on my iPad. I'm going to try from the browser.
Yeah. Heng, are you there on any of the platforms?
I can see him. He seems to be here.
He's tried to share the screen, but it appears black.
Okay.
Yeah.
And I don't hear.
Session. Interesting.
Yeah, that's a punishment for me.
Okay,
trying to go from good to excellent. So at least we could see the slides and hear him. So now we cannot do either.
all right. Okay, let me see if it works on Zoom.
Maybe play the video, pre-store the video, maybe.
Yeah, but I think we were in touch already. So it's Heng is there. So we just need to get back to him. Heng, can you hear us? Oh, okay. Now we see the slide.
Ah, okay. Yeah.
Are
Can
you,
you try to put the presentation mode, Heng?
Yes. So I can go on to present
Yeah, can you just log out from, I think you logged out in on two platforms. So just whatever you're using, keep using it, but the other ones shut it down so that we don't get audio input from two sides. Can you say something, Heng?
Hello. Hi.
Hello.
Hello.
Can
I back to the.
okay.
Can
Your
you
screen is
can you see me with my screen? Okay.
your
So I can continue my presentation.
Yeah, probably it's better this way.
Okay. Hello everyone, I'm Heng from Institute of Computing Technology at Chinese Academy of Science. I'm going to present our work, Misconfiguration checking for SDN, data structuring, series and algorithms. This is a joint work with University of Sarawak. First of all, I will introduce the background of this work. The context of this work is SDN. As well known, SDN separates the constraint plane from the data plane through open source-bound APIs such as OpenFlow. This separation not only can simplify the network management, but also enables network innovation both in constraint plane and the data plane. However, it still had to develop and maintain a complex SDN application. To address this challenge, recently, network researchers began to borrow the sort of moderations to program the network and introduce compositional SDN. Consequently, a complex application consists of multiple simple policies such as net, monitor, firewall, and so on. Network administrators somehow compose these policies by different convolutional operators to perform one complex network function. Unfortunately, convolutional SDN is helpful for two reasons. First, individual SDN policies have already been complex. This is because one SDN policy may contain one or more flow tables, while each flow table consists of a priority list of flow entries. However, each flow entries contain bitmark-based match pattern and various behaviors. As a result, it's difficult to detect the intra-policy misconfigurations. For example, the rule 3 in these figures cannot count any packet, but we don't know its relevance. Second, convolutional SDN compose different policies under different conditional operators to manage the network. But the convolutional operators are diverse, such as parallel operators, sequential operators, and overlay operators. Parallel operators enable two policies operate packets in parallel, while sequential operators make two policies process packets one after another. The override operators make one policy as a default policy for the other policy. So it's hard to detect inter-policies with configurations. For example, the highest priority rule in SP3 cannot hit any target, and it's not easy to find out the reason. Recently, some SDN verification tools such as Veriflow and PGA have been proposed for the purpose of detecting whether one policy violates the per-defined network-wide environment. But they are unable to detect the misconfigurations that don't affect the state of the network. On the other hand, a large amount of research effort has been devoted to detecting anomalies in access control policies. Unfortunately, this solution failed to detect potential misconfiguration in SDN policies. This is because they only focus on the root set with perfect basis matter and simple action such as forward or drop action. But SDN policy rules support altering bitmap patterns and complex behavior. In these papers, we decide and implement SDN policy misconfiguration management framework from the data placement. Our target is to address this gap by developing a misconfiguration tool for aggregating and fast checking of both individual policy rule set and the compositional rule set. To this end, we first define two checking principles. One is the rule available principle. It means that any rule in one policy should be useful. The other is the rule minimalism principle, which means there are no rules that can be merged. Based on the two principles, we also define two types of misconfigurations: function conflicts and development efficiency. To check policy misconfigurations, we design a normal data structure, minimal interview set. First of all, we convert the match pattern of one rule into one or more interviews. Specifically, we convert bitmap-based match pattern into binary bit sequence and compute decimal numbers. Based on these decimal numbers, we construct the corresponding interviews. As a result, for one policy, we convert each rule into a set of interviews. Next, we build the minimal interview set representation for one policy, which contains one or more interview sets. For any two sets, their match range are non-overlapping. Therefore, one rule may belong to multiple sets. Moreover, rules in one set are ordered by their priorities, and the match space of one policy is the unit of the range of the minimal interview set. Based on the above principles and the data structures, we can check misconfiguration very fast. First, we show how to check intra-policy misconfiguration. More specifically, one rule may belong to multiple interset. In at least one set, this rule should be at the highest priority root. Otherwise, it will violate the principle one. Next, we will check that whether two or more rules are manageable or not. If the answer is yes, it obviously violates the principle two. Next, we will show how to check inter-policy misconfigurations. Consider two policies SP1 and SP2. We assume that they do not have any misconfiguration under the all input space. For the parallel operator, we just check that whether the match space are identical or not. If they are not identical, we can say they are inter-policy misconfigurations. For the sequential operators, we use the change in the input phase by the parallel policy to check the later policy and detect whether the later policy contains misconfiguration or not. For the override operators, we merge the two policies, then we check the generate policy and decide whether they are intra-policies misconfiguration or not. Finally, we will show how to decide two complex action lists are equivalent or not. We abstract each rule of one policy to a function. For example, bucket P, who hit this rule in the input. This function will generate 0 or more bucket pairs and some static data. We define the bucket pairs P and the point, as bucket P appears on the corresponding point. From this, we can simply define the notion of action list equivalence. For any two action lists, they are equivalent if and only if they can generate the same output with any input bucket. Okay, next we evaluate our approach. we implement our checking algorithm and integrate them with Kave. Kave is a combination of hypervisors. We also use two types of rule set. One is a synthetic rule set, which is generated by Classbench. The other is a random rule set. First, we break down the checking intra-policy misconfigurations. It shows that the interval generation step costs hundreds of milliseconds at most, while milli-interval generations only consumes tens of milliseconds. In addition, checking misconfiguration leads to 50 milliseconds at most, while the action equivalence computations cost tens of milliseconds. Therefore, the overhead of the interval generation is the most expensive. Finally, we evaluate the overhead of checking inter-policy misconfigurations. We build a computational SDN application which involves all the three types of operators. More especially, we evaluate the cost for checking computational application with tens of policies. Each policy contains 15 or 100 rules from the two types of rule set. Nevertheless, checking 15 computational policies requires less than 2 seconds. In summary, in these papers, we consider the SDN's intra and inter-policy misconfiguration. To this end, we propose two principles for misconfiguration checking and design minimal interview set to simplify rule set presentation. Finally, we implement misconfiguration checking algorithms to detect misconfiguration very fast. Thank you.
Thank you, Heng. I'll open the floor to questions. Does anyone have any questions? Please. Actually, I'll start off with clarification. Could you please go back to slide 8?
8? Okay.
Yeah. 7 or 8. You moved too quickly. I'm not sure.
8?
Yeah.
Page 8?
Yeah.
Okay.
So I just want to clarify the second point. When you say there are no rules that can be merged, or do you mean to say there are no rules that cannot be merged?
Yes, it means that your policies, in your policies, if the two rules can be merged into one rule, we say it will violate the second principle.
Okay, I'm still a little unclear. Do you mean that you can merge all rules?
Sorry?
Does that rule that you have put out there mean that all rules can be merged?
Yes. I mean, we need the minimize rule set, because in computational SDNs, different rule set will be compared into one rule set. If there is a redundant root in one rule set, finally it will generate many redundant rule set rules in the finally generated rule set. So considering the limit resource in the switch or test plan, we don't want to generate many redundant rules. So we propose the two simple two.
Okay. Thank you. So if no one has any other questions, I will ask him one more. Okay, seems like no one has any questions. In the same slide, you talk about deployment inefficiency. Could you elaborate a little more on what you mean, not what you mean by deployment inefficiency, but what inefficiencies you're looking at from a deployment perspective?
Efficiency means generate many generate redundant rules in this papers.
Okay, but just having redundant rules is, I mean, what can you quantify that? Is because just a few redundant rules does not necessarily always mean like inefficiency. I mean, a little bit, yes, but is it serious enough to warrant the problem? It's more like a motivational thing. So if you're right now saying deployment inefficiency is part of the motivation to do misconfiguration checking, then like it needs to be a little more than a few redundant rules.
Because if two or more rules can be used, use one rule to replace this rule, so we can use only one rule to be deployment to network. So we think use many redundant rules is one type of misconfiguration.
Okay, got it. Thank you. Any other questions? Okay, if there are no other questions, then I will let's move on to the next paper. That is speed. Our author and presenter is Xiang. So Xiang Chen received his BS degree from Fuzhou University. He's currently a research assistant at Peking University and Pencheng's lab at Peking University. He's a second-year master student. He's also a second-year master student at Fuzhou University. His current research interests include programmable networks and NFVs.
Okay, thank you.
Zhang?
Do you see my slides in the presentation mode?
Yes.
Okay, thank you. Okay. So thanks for the introduction. I'm Xiang Chen, a student from Peking University. Today, I'm going to present our paper, Speed, Resource Efficient, and High-Performance Deployment for Data Plane Programs. This is a joint work by Peking University, Pencheng Lab, Fuzhou University, Zhejiang University, and the Zhejiang Lab. In programmable networks, the data plane and the control plane are separated. In data plane, there exist many programmable switches, such as barefoot Tofino switches and the Broadcom Trident switches. Moreover, the control plane runs many network management applications, such as traffic monitor, network security, and traffic routing. These applications typically install their configurations on underlying switches via data plane program deployment. Specifically, they generate their data plane programs like P4 programs that describe their logics for packet processing. Next, the data plane programs are input to a deployment system, such as a switch compiler that executes program deployment to transform these programs into switch configurations and install these configurations on target switches. So this paper focuses on data plane program deployment. As mentioned before, the deployment takes a set of data plane programs as input. Each data plane program is composed of many matrix action tables, or MATs. For example, this slide shows an example of a data plane program, which executes 4 MATs in order. Take the MAT ACL as an example. ACL has 2 phases, a match phase and an action phase. The match phase takes packets as input and matches the IP addresses of packets with respect to application rules. If a packet hits one of rules, ACL executes the action that forwards the packet to port 1. Otherwise, ACL drops the packet. After receiving data plane programs, the deployment aims to install these programs on programmable switches. Each programmable switch has a pipeline of switch stages for packet processing. Each switch stage offers 2 types of switch resources to support program deployment. First, it offers a region of SRAM and DRAM memory used to store MAT rules. Second, it offers several ALUs to execute the actions of MATs. The output of program deployment is the mapping between an MAT in a program and a physical switch stage. For example, after deploying the left data plane program with 4 MATs on the right programmable switch with 4 stages, each MAT is deployed on a specific switch stage. In recent years, program deployment enables many advanced applications, including software-defined measurement, in-network acceleration, and traffic route scheduling and optimization. Overall, the deployment takes multiple data plane programs as input and needs to simultaneously deploy these programs on substrate network. In this context, applications address 2 requirements. First, the program deployment should achieve resource efficiency given that switch resources are limited. For example, a switch only provides a capacity of 10 MB memory. Second, the program deployment should achieve high end-to-end packet processing performance, including high throughput and low per packet processing latency, in order to meet the tight requirements issued by applications. However, existing solutions fail to address these requirements. The first type focuses on the design of switch compilers, while the second type explores visualization techniques to deploy several programs at the same time. These solutions only support program deployment on a single programmable switch. When scaling to multiple switches, they have to enumerate every switch. For each switch, they will install as many as possible programs until the switch resources cannot tolerate more programs, and turns to the next switch. Doing so suffers from poor resource efficiency. Also, it doesn't take many constraints, such as device connectivity and traffic routing, into consideration. Thereby, their deployment solutions may result in poor performance due to frequent switches between different devices. In this paper, we aim to design a framework that takes several programs as input and deploys these programs on substrate network. The framework should make the best use of switch resources for resource efficiency and retain high per packet processing performance. However, our design faces 3 challenges. First, we need to resolve the difference between programs, or program diversity, and avoid case-by-case program deployment. For example, the program for Chunming sketch executes its MATs in a sequential order. In contrast, the program for netcache has many processing branches and processes packets conditionally. Second, we need to handle heterogeneous constraints, which complicate problem solving. Specifically, there are 2 types of constraints, including switch resource limitations and network-wide constraints. Consolidating them is non-trivial. Third, we need to provide inter-device coordination that schedules packets among different devices in order to preserve original packet processing semantics. In response, we propose speed to address these challenges. Speed has four main functionalities. First, it converts input programs to table dependency graphs or TDGs for handling program diversity. Second, it merges redundant operations among different programs to achieve resource efficiency. Third, it abstracts the network as one big switch to handle heterogeneous constraints. Finally, it offers inter-device packet scheduling for device coordination. This talk will focus on the first three functions due to time limitation. For more details, please consider reading our paper. At first, speed takes data frame programs as input and converts these programs into TDGs. TDG is a universal intermediate representation of data frame programs. A TDG is a directed graph where each node represents an MAT in the program, and each edge indicates the execution dependency between two MATs. This slide shows an example program and its corresponding TDG. We observe that the TDG can shield the details of the program. Converting data frame programs into TDGs handles program diversity and simplifies speed analysis. Thereafter, speed merges TDGs by detecting and merging redundant MATs. The motivation behind is twofold. First, it is essential to reduce overall resource usage, since switch resources are limited. Second, we observe that the TDGs of different programs may invoke the same MATs to execute the same operations. For example, here are three programs for software-defined measurement. All the three programs invoke an MAT to conduct CRC hashing on packet headers. When deploying these programs on substrate network, the three MATs that execute hashing become redundant. To this end, speed proposes to merge these redundant MATs to save overall switch resources. In this figure, after merging, speed reduces the number of hashing from 3 to 1, which reduces switch resource usage. Specifically, speed uses an algorithm based on longest common subsequence, or LCS, to merge TDGs. The algorithm takes n TDGs as input and merges these TDGs into a compound TDG, TM. Its workflow consists of n-1 iterations, each of which takes 2 TDGs to merge. We present an example to illustrate how program merging works. This example merges two input TDGs, T1 and T2. The LCS-based algorithm in speed first sorts the TDGs using topological sorting and obtains two topological orderings. It also detects all the pairs of redundant MATs between T1 and T2 by examining every pair of MATs. Next, the algorithm obtains the LCS of redundant MATs between the two topological orderings. The blocks marked in red represent the redundant MATs in the LCS. According to the LCS, the algorithm merges the two topological orderings by merging the MATs resided in the LCS. It outputs the merged TDG as the compound TDG, TM. After merging TDGs into TM, as speed abstracts the substrate network into one big switch, or OBS, to deploy TM. In detail, it first calculates the number of programmable switches in the substrate network. For example, this slide shows a network with two programmable switches, S1 and S2, each of which has 4 stages. Speed abstracts the network into OBS by consolidating all the switch stages of programmable switches. In this example, speed connects the 4 stages of S1 and that of S2 to form OBS, which has 8 stages in total. Speed executes program deployment based on OBS abstraction. The OBS-based program deployment has 2 properties. First, it separates heterogeneous constraints in two phases. Second, in each phase of program deployment, it only considers one optimization objective and one type of constraints. The OBS-based deployment brings twofold benefits. First, it simplifies program deployment and reduces the execution time. Second, it is able to achieve multi-objective program deployment. Specifically, the two phases of program deployment in speed are TDG placement on OBS and OBS placement on network. We introduce each phase in what follows. The first phase is used to place the compound TDG TM on OBS. We formulate this phase as an ILP program. Specifically, our goal is that for each MAT U of TM, we only need to find an OBS stage V to place U. The optimization objective is set to minimize the number of occupied OBS stages so as to achieve resource efficiency. Moreover, this phase is restricted by two types of constraints: per stage resource limitation and MAT dependencies. We solve the ILP problem using Groby. After placing the compound TDG on OBS, speed executes the second phase of program deployment, which is also formulated as an ILP. In this phase, we need to place the OBS on the substrate network. In detail, for each OBS stage U, we need to map U on a physical stage V. Our objective is to maximize packet processing performance, including maximizing throughput or minimizing per packet processing latency. This phase is restricted by two constraints, including one-to-one mapping between an OBS stage and a physical stage, and the related performance metrics of substrate network. We also use Groby for problem solving. More details of our formulation can be found in our paper. We give an example to illustrate how speed deploys two data plane programs. We consider software-defined measurement, or SDM. In this example, SDM deploys two tasks via speed. Both task 1 and task 2 has three MATs, A1 to A3 and B1 to B3 respectively. The first MAT is used for CRC hashing and obtains an index. The second MAT uses the index to update a sketch data structure for measurement. The third MAT simply forwards the packet. Speed detects that A1 and B1 are redundant. Thus, in the first step, it merges A1 and B1 into C1 and produces the compound TDG, TM. The second step of speed is to place TM on the OBS of substrate network. The OBS has 4 stages. After TM placement, each MAT of TM is placed on a specific OBS stage. In this step, speed guarantees that the number of occupied OBS stages is minimal, such that it achieves resource efficiency. Finally, speed maps the OBS onto the network. The network has 2 programmable switches, which are directly connected with 2 paths. The first path transfers packets at a cost of a latency of 55 milliseconds, while the latency of the second path is 32 milliseconds. The OBS placement finds the performance optimal placement on the substrate network. First, it uses the second path with the minimal latency for the communication between the second OBS stage and the third OBS stage. In this step, speed guarantees that the packet processing performance is maximum, such that it achieves high performance. We evaluate speed on a test bed comprising a barefoot Tofino switch and several servers. We also use MiniNet to simulate large wide area networks to test speed at scale. We choose 10 P4 programs to evaluate speed. 5 of the programs are used for software-defined measurement, while another 5 programs are extracted from switch.p4. We compare speed with several heuristics for program deployment. We evaluate speed to answer 2 questions. First, can speed achieve resource efficiency? Second, can speed achieve high performance? More results can be found in our paper. First, we measure the number of occupied switch stages to evaluate resource efficiency or speed. We vary the number of programs to be deployment from 2 to 5. Our results indicate that compared to heuristics, speed is able to save up to 25% switch stages. This demonstrates that speed achieves resource efficiency. Second, we measure the per packet processing latency after program deployment. We choose 2 wide area networks, AbovNet and Internet2. In each topologic, we randomly select half of the devices as programmable switches, while the remaining devices are set to layer 3 routers. We set the latency of each link to be uniformly distributed from 10 milliseconds to 50 milliseconds. We use speed and heuristics to place input programs on the network respectively. Our results indicate that compared to heuristics, speed achieves 14% to 59% latency reduction. First, speed can achieve high performance program deployment. To sum up, in this paper, we propose speed, a framework that offers resource efficient and high performance data plane program deployment. We introduce 3 designs of speed, including TDG for handling program diversity, program merging for reducing overall switch resource usage, and the OBS-based deployment that provides multi-objective program deployment. We use 10 real-world data plane programs. The experimental results indicate that for the tested programs, speed reduces the number of switch stages and the per packet processing latency. Finally, we want to thank our Shepherd and the reviewers for their constructive comments to this paper. That's all of my presentation. Thank you very much.
Thank you, Xiang.
Thank you.
I'll open the floor for questions.
Okay. So any questions?
I actually have a couple, but I'm waiting to see if anyone else has questions.
Okay, can you hear me?
Yeah, we can hear you. Don't worry.
Oh, okay.
Okay, so let me start off. I have a question regarding your OBS abstraction.
Okay.
So if I understood that part correctly, you're basically splitting your MAT and placing them across switches, right?
Yeah.
Now, if you, not your MAT, your TDGs. So if you split them and place them across switches, what happens in the case of a link failure and one switch is not reachable? What happens to parts of your TDGs that have been placed on any of those switches?
Okay, so thank you. If I understand you correctly, your question is about what will happen when link failure happens, right?
Yeah. Yes.
Okay. Actually, the current design of speed relies on a central controller to detect link failures. If link failures happens, the controller will notify administrators to reroute these packets to backup links to guarantee the communication between different switches. But in the future, we also plan to investigate more advanced techniques to handle link failures in speed. Okay. Do I answer your question?
Yeah.
Okay.
Also, this is more of a clarification. Seems like this is based on an assumption that all your programmable switches in your network are running the same program, and all of them have the same number of stages.
Yeah, we make these assumptions in the current design of speed, but we plan to investigate more design spaces in speed to tackle this problem, I think.
Yes, but okay, because at least at the second part where the second point that I mentioned,
yeah,
invariably not always true.
We plan to investigate this in the future work.
Awesome. Okay, thank you.
Thank you.
Anyone else have any more questions? Any other questions? Sergey, are you there?
Yeah, I'm here.
No, not Xiang. Sorry.
I'm here. So I think.
Do we just move on to the next one?
Yeah, I guess the virtual format is kind of subdues people activities. So everybody prefers to sit quietly in front of the computer. So, but Chunming, we have to count on you usually to ask questions here. Yeah, I think you can proceed further. I guess you don't need to make an introduction for the second time.
Yes, exactly. Okay. Xiang, go ahead and start with ApproSync then.
So can I start another presentation here?
Yeah, the next presentation. Yes.
Okay, thank you.
You're welcome.
Okay, so hello everyone. I'm Chen, a student from Peking University. I'm going to present another paper, Approximate State Synchronization for Programmable Networks. This is a joint work by Peking University, Pengcheng Lab, Fuzhou University, Zhejiang University, and the Zhejiang Lab. In today's programmable networks, the data plane and the control plane are separated. The control plane runs many applications, such as firewall and the traffic monitor. The data plane consists of many programmable switches. These switches process incoming packets with respect to the policies installed by the control plane. Moreover, they also record latest states during packet processing and provide these states to the control plane applications for making new decisions. In particular, the state represents the data plane state, which refers to historical packet processing information. Take a Chunming sketch as an example. The sketch maintains an array of switch counters to record flow counts. In this example, the state represents the set of all the counter values recorded in the switch. Since the applications that manipulate states reside in the control plane, while the states are frequently updated in the data plane, we need to synchronize the state updates between the two planes. Specifically, there are two types of state synchronization in programmable networks. First, the bottom-up synchronization, namely state read, needs to timely synchronize the latest states from programmable switches to the control plane. Second, according to received states, applications make decisions and invoke the top-down synchronization or state write to populate the policies recorded in states to programmable switches. In particular, state synchronization raises two essential requirements. First, the synchronization should be low latency to meet the tight performance requirements issued by latency-sensitive applications like anomaly detection. Second, the synchronization should minimize the value difference between the states in the data plane and that in the control plane, so as to retain high accuracy for applications to make correct decisions. However, existing solutions fail to meet the two requirements. The first type is based on the operating system of each programmable switch, referred as switch OS. The switch OS first collects all the latest states from underlying switch ASICs via PCIe channels. Then they transfer these states to the remote control plane via reliable TCP connections. However, the bandwidth capacity of PCIe channels and the TCP connections is typically limited and below 100 gigabits per second. The switch OS transfers all the state updates each time, such that the amount of consumed bandwidth can reach several hundreds of gigabits per second. This results in high latency in state synchronization. We conduct a benchmark experiment to measure the latency of switch OS. We use a barefoot Tofino switch and deploy an array with 2 to the power of 16 counters. We collect these counters via switch OS. We observe that the switch OS spends several seconds to complete the state synchronization, which is unacceptable for most applications. The another type is traffic mirroring. It bypasses the switch OS and directly mirrors state values from switch ASICs to the control plane. This avoids the overhead in the switch OS and achieves low latency. However, the link used for traffic mirroring has limited bandwidth capacity. Transferring all the state values leads to an extremely high sending rate, which overloads the link. To validate our claim, we conduct a benchmark experiment to measure the state loss in traffic mirroring. We establish a simple test bed with one programmable switch directly connected to a server. We use traffic mirroring to collect 2 to the power of 16 state values from the switch to the control plane via a 14 gigabits per second link. We conduct the experiment under a high input traffic rate, which varies from 14 gigabits per second to 120 gigabits per second. We observe that in the worst case, traffic mirroring loses 60% state values, which makes the state synchronization highly inaccurate. We also evaluate the impact of existing solutions on the accuracy of an application heavy hitter detection. Our results indicate that the high latency in switch OS and the state loss in traffic mirroring seriously affects the accuracy of an application. More details of our benchmarks can be found in our paper. So here we face a question: can we achieve both low latency and high accuracy in state synchronization? Obviously, we can refer to traffic mirroring and bypass the overhead of switch OS to achieve low latency. However, achieving high accuracy is challenging. As mentioned before, directly transferring states between switch ASICs and the control plane faces the problem of state loss due to limited link bandwidth. Meanwhile, it is impossible to adopt existing solutions for high reliability because of switch limitations. For example, realizing retransmission entirely in switch ASICs is infeasible, given the total memory capacity of 10 MB. First, the main challenge we need to resolve is how to handle the state loss, even with link and switch limitations. This challenge motivates us to dive into the requirements issued by applications to design a workaround. After investigating many applications that require state synchronization, we found an interesting observation. Network management applications typically tolerate a small state divergence. Here, the state divergence indicates the value difference between the state in the data plane and the state synchronized to the control plane. For example, assume the state value in data plane is V1, and the state value synchronized to the control plane is V2. V1 equals 100, while V2 equals 99. In this case, the state divergence between V1 and V2 is 1. According to our experiment, for the selected 3 applications, a state divergence of less than 1% only leads to application level error of 2%. Such a small error is acceptable. Motivated by our observation, we propose ApproSync that offers approximate state synchronization. The design of ApproSync bypasses the switch OS to achieve low latency. Also, it allows a small but acceptable state divergence. That's to say, it permits a small but bounded error in state synchronization. Doing so will elevate the resource overhead incurred by transferring states and avoid state loss. First, ApproSync can achieve both low latency and high accuracy. The key design of ApproSync is the hash table resided in the switch ASIC. The hash table has two main functionalities. First, the hash table directly aggregates the state updates inside the switch ASIC. For example, suppose that there are two packets, A and B, update the same counter in a counter array. Packet A triggers a state update that changes the value to 1. Packet B also triggers a state update that updates the value to 2. We assume that the link connected to the control plane only supports synchronizing one state update at a time. So if we directly send the two state updates to the control plane, just like what traffic mirroring does, the link is congested and the state loss happens. To avoid state loss when synchronizing state updates, the hash table aggregates the state updates that access the same switch counter. For example, the two state updates incurred by packet A and packet B update the same switch counter. So they are merged into one aggregated update that changes the state value into the final result 2. In this way, the hash table reduces the amount of state updates to be synchronized, which reduces link load. Although aggregating state updates reduces link load, it introduces the difference between the states in the data plane and that in the control plane. Since the applications require high accuracy, we need to keep the state divergence small. First, we design the hash table with the second functionality that bonds the state divergence during synchronization. Specifically, assume the latest state value in the data plane is V1, and the current state value maintained by the control plane is V2. The hash table can guarantee that the divergence between V1 and V2 is smaller than a threshold T. Here, we give an example of hash table. In this example, our goal is to synchronize value 1 between the two planes. In the data plane, we employ the hash table with several entries in the switch ASIC. Each entry of the hash table stores a specific state update to the counter values. Each entry has 3 properties. The first property, location, represents the counter identifier. The second property, value, equals the latest state value in the data plane. The third property, old, refers to the last state value synchronized to the control plane, which equals the state value in the control plane. When the first packet comes in, the switch updates value 1 to 1. It generates a state update and inserts it into hash table. At the same time, the hash table calculates the state divergence as the absolute value of the difference between the state value in the data plane and that in the control plane. The state divergence is 1 in this case, which equals the threshold T. The hash table chooses not to synchronize the state update because the state divergence is small. Next, the second packet comes in and triggers another state update. The update is inserted into the hash table. Meanwhile, the hash table detects that the current state divergence between the data plane and the control plane is larger than the threshold T. So it immediately synchronizes the state update stored in the first entry to the control plane to keep the state divergence small. This example gives two takeaways. First, in the situation without hash table, we need to synchronize all the state updates, which may lead to state loss. In contrast, with hash table, we only need to synchronize one aggregated state update. So the first takeaway is that our hash table can reduce link load and avoid state loss. Second, the hash table also guarantees that the value difference or state divergence between a state value in the data plane and its copy synchronized to the control plane is always smaller than the threshold T. This bonds the state divergence and enables applications to work on accurate state values. In addition to the hash table, ApproSync also provisions other advanced features, including rate control that adaptively tunes the threshold of hash table based on real-time traffic rate, and the reliable and atomic mechanism for top-down state synchronization or state write. Due to time limitation, we don't dive into the details in this talk. Please consider reading our paper for more details. We have implemented a prototype of ApproSync on built Tofino switches using P4 language. Our prototype provides two-state synchronization operations to network management applications, including state read and state write. We evaluate ApproSync on a real test bed. We choose an 1-hour KDA trace and the 16 stateful P4 applications to evaluate ApproSync. We compare ApproSync with 3 methods: switch OS in our Tofino switches, traffic mirroring, and the star flow. Star flow is a variant of traffic mirroring that uses an LRU cache for rate control. We evaluate ApproSync to answer 2 questions. First, can ApproSync achieve low latency and high accuracy in state synchronization? Second, can ApproSync bring benefits to real applications? First, we evaluate that ApproSync achieves low latency state synchronization. We use ApproSync and the switch OS to collect state values from a programmable switch to the control plane, respectively. The left figure indicates the result of collecting 16-bit state values, while the right figure represents that of collecting 64-bit values. We found that compared to switch OS, ApproSync achieves order of magnitude latency reduction by bypassing the overhead of switch OS. Second, we evaluate that ApproSync offers accurate state synchronization. In the left figure, we present the measured loss rate of state values during state synchronization. There are 2 situations. First, without ApproSync, the state synchronization of traffic mirroring and the star flow loses around 18% state values, which is unacceptable. Second, with the hash table of ApproSync, ApproSync is able to achieve loss-free state synchronization. Note that here we vary the threshold T of hash table to study the impact of ApproSync. Indeed, our design of ApproSync will adaptively tune the threshold T with respect to the real-time traffic rate. It guarantees that no state loss will happen at runtime. For example, as shown in the right figure, even if we inject traffic at 200 gigabits per second, ApproSync ensures that no state loss will happen. Next, we study the impact of ApproSync on the 16 stateful P4 applications. We deploy these applications on a Tofino switch respectively and use ApproSync to read or write switch control values at runtime. We compare ApproSync with the switch OS. As shown in this figure, ApproSync achieves order of magnitude lower synchronization latency than the switch OS. We also evaluate the impact of ApproSync on the application level accuracy. We select the Chunming sketch as an example and use ApproSync to read 2 to the power of 16 sketch counters from the Chunming sketch running on a programmable switch. In the control plane, we run a heavy heat detection as the application. We compare the accuracy of ApproSync with that of traffic mirroring and the star flow. Our results indicate that ApproSync can achieve near ideal application level accuracy, while other solutions suffer from poor accuracy due to serious state loss. In summary, this paper targets the problem of state synchronization in programmable networks, including high latency in switch OS and low accuracy in traffic mirroring. We face the challenge of handling state loss entirely in the switch ASIC. To this end, we first present our observation that most network management applications tolerate a small error or state divergence during state synchronization. Motivated by our observation, we design ApproSync. ApproSync bypasses the switch OS to achieve low latency. For high accuracy, it uses an in-switch hash table that aggregates similar state updates to avoid state loss and bonds the application level error. Finally, we want to thank all the committee members of ICMP 2020 for their excellent efforts in making this year's ICMP successful. Especially, we want to thank our shepherd and the reviewers for their constructive comments to this paper. And that's all of my presentation. Thank you very much.
Thank you, Xiang.
Thank you.
Floor is open for questions.
Okay, any questions?
Okay, I have one. So in your hash table,
Okay.
the information that you are storing is the value that is changed and what was the old value that was sent to the controller, right?
Yeah, you're right.
So how do you know if the old value that was sent to the controller is actually the value on the controller itself? What if that state packet was lost, delayed, anything? How do you handle a case where there is a mismatch there, or there may be a mismatch there?
Okay, that's a good question. In current design of ApproSync, we assume that the hash table stores the last state value sent to the control plane equals to the value stored in the control plane currently. But I think this is a good question, and but in the current design of ApproSync, we didn't tackle this problem in the current design. So I think maybe we can investigate this direction in the future.
Okay.
Okay, thank you.
No, you're welcome. Actually, a follow-up on the same lines is you spoke about state reads and state writes as the way you do things, right? So assuming state writes, do you guarantee atomicity of operations? Like what happens if you lose packets in between? Do you roll back the entire thing, or how do you manage the state update in that case?
Thank you for your question. I'm afraid I don't understand. Could you repeat your question, please?
So in a state write, what happens?
State write?
Yeah, state write.
Okay.
What happens when? What happens if state update packets with new states stop arriving? in the middle. So let's say you had a bunch of state updates. You have reduced the number of state updates that actually need to happen, but you still have like some state updates, right? And you receive some state updates, but then something happens and you stop receiving the rest of the state updates. So what happens to the ones that have been committed, but the ones that have not been received? So do you roll back in some way? How do you solve that problem?
Thank you. If I understand you correctly, your question is about how ApproSync handles new arrival state updates during state synchronization, right?
Not exactly. So if you miss or there are out of order state updates during state synchronization, what happens then?
You mean state update loss?
Yeah.
Okay. So in state write, the synchronization is driven by the control plane. So we can realize some reliable solutions in the control plane. For example, we can detect the lost data updates during synchronization using, for example, ACK mechanisms, and immediately retransmit these state updates once these updates get lost. So
correct. And my question was more like, what are you doing? I understand you can do this from the control plane, but are you doing this? Have you done this? Because design number 3 says reliable and atomic state writes. So when you say an atomic state write, it means that you guarantee that your state writes are going to be committed in an atomic manner. But what if you miss some state updates? Do you roll back those ones that are already committed? So that's what I'm trying to understand.
Okay, so I think I'm sorry, I still don't get your point. So could you please send me the question after?
Yeah, I will send you the question. Yeah, don't worry,
okay,
we'll take it off.
Thank you very much.
No problem. Yeah.
Thank you.
Yeah. Any other questions? Sergey, there don't appear to be any questions. Do you want to? Oh, is Sergey even here? Sorry.
Actually, Sergey is gone.
Sorry, Sergey is gone. Sorry. So what do we do, Leonardo? Do we just end?
Well, actually, if no more question, if nobody wants to add something or ask other question, I think that we can stop here.
Okay.
So yeah.
Last call for questions.
We will have a pause of 1.5 hours, and then we will come back with the next session. So, by the way, I don't know, we can wait here for the last 10 minutes. Maybe someone jump in and wants to ask something, or I don't know. We can just wait, maybe.
Sure. Yeah, we can wait. For the timing, thank you so much, Heng and Xiang, for your presentations. We'll just hang on here in case someone has any questions.